We said that one way to think about energy is the capacity to do work. And the easiest form of work to visualize is mechanical work. And the way you have come across mechanical work earlier is in your physics lessons, where you've learned that work is done when an object is moved by a distance d, when it's opposed by a force F, such as gravity, for example. So work, what you've seen before, is force times distance. And if you want to be more precise about it, it's actually, work is the scalar product of the force vector and the displacement vector. So if you have, so that will be F times d cos of theta, where theta is the angle between the force vector and the displacement vector. So let's say you had an object that's placed on the floor and there is a force acting on it in this direction, and the object moves in this direction. If you have to calculate the work done, you just take the component of the force in this direction and then multiply it with the distance or the displacement. So that's why you have the scalar product between the force vector and the displacement vector. So in any case, so this is how you've come across work earlier. So in thermodynamics, we'll actually focus on work done during changes in pressure or the volume of the gas, and what we call the pressure volume work, or the PV work, pressure volume work. This is also called PV work. And to describe this PV work, we'll use some imaginary setups, and these setups will have a container, an enclosed container with gas in it, with a piston, and the piston is actually a frictionless piston, and you assume that the gas inside the container is an ideal gas. So remember how I said in a previous video that this enclosed container with a gas it's a common scenario you'll come across in thermodynamics. People will keep talking about frictionless pistons and ideal gases. So a setup like this, basically. So what we need to realize here, that real life scenarios where one really applies the principles of thermodynamics are very different from these ideal oversimplified situations. These you're not going to find a frictionless piston in the real world. You're not going to find a truly ideal gas. All the pistons that you will see are going to have some amount of friction, and the gases that you will come across are all real gases. When we say we assume this gas to be ideal, what we mean by that is these molecules or atoms that are shown here do not interact with one another at all. They don't talk to each other. They do not have any kind of interatomic or intermolecular interactions. So even if you compress it to a small volume, what you assume is that this ideal gas, these molecules do not have any interactions whatsoever, and that's not true in real life situations. So the reason these simple models are in place, because they act as limits or boundaries or reference points for us to predict the behavior of a system in a real life scenario. So real life scenarios are very, very complex, but we have to start somewhere to try and understand them. So we imagine these simple problems and solve them, and then use those solutions to guide us to solve more complicated problems with more variables. So whenever you see these problems in thermodynamics or any other topic, like for example, this ideal gas enclosed in a container with a frictionless piston, you must remember that all these imaginary setups are devised by people like you and me. That is the scientists that said, okay, let's assume we have something like this and then solve this problem. We'll worry about other complexities later. So I know we have digressed a little bit here, but I want to tell you that you should not be, carried away by these models or theories. You just need to know that they have been formulated by scientists for our convenience and easy understanding of the universe. So it's not the other way around. It's not like these models always existed, somehow, and they, people have said that this is how things work, and it's not like that. Okay, so coming back to our imaginary system here, let's say the initial internal pressure of this gas that is enclosed in this container with the piston on one side, let's say the pressure here is P internal, and let's say the initial volume of the gas is VI. And the external pressure that's being applied by the surroundings on this system is denoted by P external. So if P external is equal to P internal, then the system is at equilibrium. So nothing is going to happen, nothing is going to change. The piston does not move, and there is no work done here. But let's say if the external pressure is actually higher than the internal pressure, then what will happen is the piston actually moves inwards and compressing the gas, and the final volume of the gas is lower than what it used to be to begin with. So in this case, we say that the surroundings have done work on the system. So let's say in the case where the internal pressure is more than the external pressure, then the ideal gas will actually expand, causing the piston to perform work on the surrounding. And final volume Vf will in that case be greater than Vi. So basically when the pressure, the external pressure is higher than the internal pressure, work done is by the surrounding on the system. And when the P external is lower than P internal, work is done by the system on the surroundings. So just keep that in mind. So to calculate the work done here, so we go by our definition, work equals F times D, and we know that the force exerted on the piston is going to be the pressure P external times the area of cross section of the piston. So pressure times area gives force times the distance that is moved, that the piston moves in response to the differential in the pressure. So this is your work done. The distance here is delta H, as you can see. So delta H, P external times A times delta H. So that will be, so in this case, HF minus HI, that's the delta H, and this is negative if the surroundings are doing work on the system, because the final volume is actually lower than the initial volume. And we know that a volume of a cylinder is area times height. So this will be, this you can, if you open up these brackets here, what you will get is AHF minus AHI, which will be Vf minus Vi, Vf minus Vi. So that is, so this is what we mean by the PV work. So it's the external pressure, the pressure against which the piston is moving, and at times the change in volume. So next I want to tell you about the convention that is generally used in describing positive and negative work. If work is being done on the system by the surroundings, then work done should be positive. And if the system is actually doing work on the surroundings, then work done is negative. So that is just a convention, and you might come across conventions that are completely opposite of what I just said, and you shouldn't be confused by that. But what we are going to follow in this video and in the series of videos from now on is we are going to call the work done on the system by the surroundings positive. So in this case, the surroundings is actually doing work on the system, and your final volume is actually lower than your initial volume. So delta V here is negative. So to make this work positive according to the convention we have agreed upon, you need to add a negative sign here. So this becomes negative P external times delta V. So this is work done on the system surroundings. So similarly, when you talk about Q, which is the heat transferred, you say Q is positive when there is a transfer of heat from the surroundings to the system. So again, you're following a similar convention here as work. So when heat is transferred to the system from the surroundings. So another thing to note here is that the units of work, heat and energy are all joules. So that is how when you say delta E equals Q plus W, all of them have the same unit. All have units joule. So they are all equivalent in that regard. So the last thing I want to cover before we end this video here is work is not a state function, and I've mentioned this earlier. We know that internal energy is a state function. It actually does not depend on what how a state is reached or what pathway you take to get from one state to the other of the system, but we'll see here that work actually depends on the pathway that you take to go from one state to the other. So what I've shown here are two pathways. Let's say this is a gas enclosed in a container. This is a PV diagram, and you'll come across these diagrams quite a bit in thermodynamics. So if you notice, the initial state is this red dot, and that is represented by a point on the PV diagram. So what you can tell here is that the gas initially to begin with is at a volume V1, and at a pressure P1, and the blue dot here is represents the final state of the system. So this is where it has to get from the red dot to the blue dot. So to do that, it can either pick pathway A or pathway B. And what we mean by that is it can go from red to yellow, yellow to blue in this case, or it can go from red to pink and pink to blue. So here what's going on is the gas is actually expanding from V1 to V2 because the volume is increasing, as you can see. So if you see this, here is V1, that is V2. So but the gas remains at a constant pressure. So the pressure doesn't change, still at P1, but the volume actually goes up. And then from yellow to blue, the volume remains constant, but the pressure is actually dropping from P1 to P2. So this is how it gets from its initial state of V1 P1 to V2 P2 final state. And here, if you notice, when it's going from V1 P1 to V2 P1, the work done in this case is P1 times delta V. So that is going to be the area of the rectangle that's represented by this box here. So the area of this rectangle here is going to be equal to P1 times V2 minus V1, which is delta V. So that is the, and going from yellow to blue here, work done is 0 because your delta V is 0. The final volume minus initial volume in this step is 0. So the work done in this part of its journey is 0. So the total work done is only calculated as P1 times V2 minus V1. So that is your pathway A. Now if you take the next pathway, here it's going from a volume P1, which is the same as what it was here in this case. Now it drops the pressure from P1 to P2 at a constant volume. So the volume of the gas doesn't change in this step, in the step 1. And then in the step 2, it actually goes from volume V1 to V2 at a constant pressure. So the volume actually increases in this step. So work done in step 1 here is 0 because the delta V here is 0. But work done in this step is going to be this rectangle here. So if I can, so this is going to be P2 times V2 minus V1. So here the work done is, so if I can, so P2 times V2 minus V1. And in this case, work done is P1 times V2 minus V1. So you can clearly see that work done from going from the initial state of this red dot here on the PV diagram to the blue dot here is much higher in this case versus in this case. So it definitely depends on what path the gas actually takes to go from its initial to final state. But on the other hand, if you take a property like internal energy, that is between the initial red dot and the blue dot states, the difference in internal energy is going to be the same for both this pathway and this pathway. So internal energy is a state function, but work is not a state function. So work is not a state function.